Good morning, good afternoon, and good evening to all our attendees joining us today for this latest Data Science Central webinar. This is Bill Vorhies, your host. I'm the editorial director with Data Science Central and also chief data scientist for Data Magnum. I'd like to start off our event today by thanking Tableau for sponsoring today's event. Tableau's a longtime supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. I'd also like to take this opportunity to mention and show our appreciation for some of our other recent sponsors, including Pivotal, Microsoft, Hortonworks, Oracle, IBM, and Teradata, to name just a few. Past webinars are available on demand at datasciencecentral.com. If you haven't had the opportunity to view them, I encourage you to take a look. They provide some very useful insight into a wide variety of topics of interest to our data science community. Today's webinar is entitled, How Do We Know That? An Introduction to Visualization Research. And before we begin, I'd like to briefly review the format of today's webinar. Today's event is an hour long. We'll have one panelist that I'll introduce in a minute. There'll be a 10 to 15 minute Q&A following the presentation. And this event is being recorded and will be available on datasciencecentral.com in the next few days following today's live event. I'd also like to encourage all of our attendees to provide questions throughout the presentation. We'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. I'm very pleased to introduce today's speaker, Robert Kosara of Tableau. Robert's a research scientist at Tableau Software and formerly Associate Professor of Computer Science at UNC Charlotte. He has created visualization techniques like parallel sets and performed research into perceptual and cognitive basics of visualization. Recently, Robert's research is focused on how to communicate data using tools from visualization and how storytelling can be adapted to incorporate data, interactions, and visualization. He received his Master of Science and doctoral degrees in computer science from Vienna University of Technology in Vienna, Austria. Thanks for being with us today, Robert, and we're looking forward to your presentation. So, pie charts are bad, right? Bar charts are good, but stacked bars aren't. And there are a lot of other things you haven't heard of. But how do we know those things? There's a very active research community that's looking into these questions and trying to find out what works and what doesn't work, how well we can see and compare certain things. In today's DSC webinar, we'll give a brief overview of some of the early roots of visualization research, as well as some of the very fundamental research that has led us to where we are right now. In addition, we'll show you some of the open questions that we're only starting to address. So Robert, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Thank you, Bill. So welcome all to this talk, and hello from Sevilla. I'm currently in Spain, which is making this quite interesting, and it's an interesting time of day for me. So this talk today is about how do we know that? How does visualization research even work? How do we learn new things about data and data visualization? And I want to walk you through, as Bill just read you this little introduction or description of the talk. I want to walk you through a few examples and show you the mechanisms of how research works and show you some of the kind of, maybe not classic works, but important works in this area, and also some recent works. I'm going to focus on the recent research to show you a little bit of what's happening in this community, not just things that are 30 years old. However, anyway, so I will show you some of those older things. So here's a pie chart, and you've all seen pie charts. I like this particular example because it's so obviously bad. This is actually taken from Wikipedia. It's the list of states and territories in the U.S. That's 56 slices on this pie chart, and they're sorted here and sized by their population. And it's clear that there's just way too much information here. It's clear that this is hard to read. But how do you quantify that? How can we make an argument that's actually scientific, where we can show that this doesn't work, where we can also maybe perhaps, hopefully actually understand how it works, how we read pie charts, and from that understand how we should make them or why we should or should not make them. And I will come back to this a little bit later, but I don't want to focus too much on this particular kind of work, but this is very important for us because this is a technique that's used a lot. Here's another example that is a bit different. This is a very old chart. This was done by William Playfair in the very beginning of the 19th century, or at the very beginning, I guess, of the 19th century. This shows the imports and exports between England and Ireland. So the bottom line here is, there's a time series here that the time axis goes from 1700 to 1800. And the bottom line here is imports from Ireland, and the top line is exports to Ireland, at least for the most part, it's the top line. And the gray area, sorry, this brownish gray area there, is the difference between the two. And it turns out that throughout most of the 18th century, this was in favor of England. So England was exporting more than it was importing. Now, what you want to get from this is you want to actually read the difference between those two lines, right? This is a very straightforward kind of chart today. It was really new and novel at the time. But what's interesting is that even when you know some of the problems, it's really hard to actually read this precisely. So what you're supposed to do, if you're looking at the distance here for 1760, for example, is you're supposed to look at the vertical distance between those two lines. But in reality, you read it more like this, because you're looking at this as if it were a river, and you were looking at the width of that river. And of course, which means that the line is basically going across at a right angle to the main direction of that area. And that's a problem because this is a very basic chart, and we're making a mistake. So at the bottom here, you can see the difference between those two lines. And this gets even more extreme when we look at 1790 here, where the vertical distance is very high, but the overall direction of this ribbon is also kind of going up. So it looks like it's actually, this might be more, the blue line might be more of what you would expect the distance to be. And that is more than a factor of 2 difference, actually. And there's been some recent work, actually, in this area. I'm not going to talk about that in particular, but people have been starting to look into this and try to question how well we can actually read charts and also what to do about that. How can we make that better based on some of the things we know? This particular effect here is a very basic one in psychology. It's called the line width illusion, but there are many that are actually much more specific to data visualization, and I'm going to talk about those a little bit. But first of all, I want to talk a bit about kind of the general idea of research in data visualization. What does it even mean? Because it's a very kind of strange kind of science, right? It's not a natural science like physics, perhaps, where you have instruments that you can use to look at things like stars, and you can have theories that you can build and where you can write down equations, and those equations give you a way to predict things, and then you can test those. You can find out if they actually describe what the world is actually like. And if your evidence doesn't contradict that, then it looks like it's a good theory. But if it happens to contradict that, then you have to figure something else out. So there's a mechanism for how you do research. It's a bit simplified here, of course, but there are ways that are fairly well understood today, and there's a good method for that, a good structure. There's also we don't have the problem, of course, in visualization that we don't see things. So if you're doing microbiology and you're looking at microorganisms, you need tools to do that. You need instruments. This is not our problem. We can see the things, but we still need to figure out how do we actually understand what's going on. How do we improve that? And what visualization actually is of course, it's its own field, hopefully, but it's also a big agglomeration of different things. There are a lot of different fields that play into it. There's computer graphics because we use pixels and we create pictures, right? There is statistics because we deal with data and we try to understand what's in the data, what the data tells us. There's perception because we look at those pixels that we've generated and we need to understand how that works, what we can actually see, what we cannot see, and so on. And then there's cognition, which is the understanding of the actual data and of the pictures that we're looking at. And we need to understand, what do we learn from those? How do we use them to actually then make decisions and so on? There's what's called HCI, human-computer interaction, which is we're not just looking at static images, we're working with them, we're changing filters and settings and the way the data is displayed. And that is a very complex interaction, a very complex way of working with things. But we need to understand how that works, and there's a whole field that goes into that. And then, of course, there's also engineering. We're not just observing what's going on, we are building things. So it's really a science as much as an engineering field. And then there are other things that I'm not even going to talk about today, like databases and lots of other things, because of course we need to get to the data to visualize it all, and we need to understand all sorts of things about how we make it faster and how we can slice data in different ways and how to make that work correctly and so on. So there's lots of science behind that as well, which I will not even get to. But so there's more to it than just the obvious things. And I want to talk very briefly about this engineering aspect of data visualization. So this is an image of the first tree map. This is from the original tree maps paper that was published in 1994, I believe. If this doesn't look familiar at all to you, and you say, well, I've seen tree maps, they don't look like this, and this is because this is the earliest. This is the way it looked at the very beginning. And this shows you Ben Schneiderman's hard disk, actually, and his main documents folders, I guess, and how they were separated, what they contained. And this was a good technique. This was a good idea at the time, but people keep building on things. The original tree map was much more about a tree structure and kind of a deep structure, but over time, people have improved it and built on it and made it into something quite different. Today, you're more likely to see something like this, which is a map of the stock market. And I chopped off that URL there, but this is a website called FinViz with a C at the end that just came out with this new map of the market that was at Smart Money earlier, that shows you all the stocks. It sizes them by their market capitalization. It shows a color here for change, and you can interact with that. You can mouse over it. It'll give you more details. You can zoom in and so on. So this is the way more people today actually use it, and I'm hoping to use this to kind of illustrate how things change in terms of engineering. So somebody has an idea, they publish that in the literature, and then somebody else says, oh, this is nice, but what about this? What about that? And then they try out lots and lots of different things. And then they all say, well, here's a new thing that's better. But it's not, and sometimes, I mean, in this case, it's clear that this works really well for this case, so there's no debate about this. But there are probably hundreds of papers about tree maps alone. There's certainly hundreds of papers about parallel coordinates, for example, and how to use them differently and what to do better and so on. And there are lots and lots of other things that people have done to work on techniques and improve them and change them. So how do we know that a new thing is actually better than an existing thing? And to talk about this, I'm going to use a model that was created by Tamara Munzner, who also just has a new, well, it's not just, but she has a book published not that long ago, in last year. We'll talk about that at the very end. And she has this very nice model of the different kinds of things you need to understand and to do when you're evaluating a new technique or something that people do in data visualization. And this is what she calls a nested model. So it has these different items that are dependent on each other. The innermost part here is this purple one is what's called the algorithm. So this is what actually does the actual computational work to get something on the screen. And this is not what I'm going to focus on. I just want to briefly mention it because it's important, certainly when you're dealing with large data or when you're dealing with complex data. I entirely left out, by the way, the part that talks about what's called scientific visualization, where you might have geometrical modeling and so on. And there, it's very important to have algorithms that can actually be fast enough and efficient enough to actually work with the data that you need to do your analysis with. But the algorithm is something we understand fairly well because it's a computer science thing. So we know how to analyze an algorithm in terms of its runtime, in terms of its memory use. There's always this trade-off. Sometimes things go faster when they use more memory. Sometimes you can't use more memory, and so on. And then there's what's called computational complexity, which tells you essentially how much slower something gets if you add more data to it. And that's an important factor as well, because if you test it on small data and then you scale up, you want something that actually scales well and doesn't get too slow. But either way, this is computer science, and this is the part that's really understood really well. But Munzner's point is also here is that sometimes we try to use those metrics for computer science when we actually care about something quite different. And those different things are actually the ones that are more interesting to me. For example, that green box here, which is just around the algorithm. This is about visual encoding and what she calls the interaction idiom, or the visualization technique. How do you get the data on the screen? How do you turn those numbers into something that's visual? And that is a design question. You have to draw something, and you have to figure out what that's going to be like at the beginning, and then you have to test it. And to test it, the main tool is, she says, cognitive psychology. Here I would add perceptual psychology, because there are these two elements: perception first, which is kind of the basic perceptual part, and then cognitive psychology, which is more about the understanding. But both of those are important to understand and to measure how well can people actually work with this. Can they solve a task with this? Can they even see the differences, for example? Like if you're using color encoding, will they be able to actually see that? Will they be able to tell 15 different colors apart and so on? And that's actually pretty hard to evaluate. And there's very sophisticated techniques for doing just that, for just building study tools. And then the othermost part here is about what she calls a domain situation. And this goes into anthropology and ethnography, where you want to understand how people even work. What are their needs? What are their tasks? What are they trying to accomplish? And then at the end, also, if I set you down with my new cool little tool and let you use it and observe what you're doing, and then maybe try and measure how well that works, and maybe it turns out to actually work well, then I would, and then maybe I come back 2 weeks later and see, does this even work at all? And maybe you've never even touched it in the meantime, then that's a problem. Then I did not succeed. So there are different kinds of or different ways of measuring success here that are quite different. So let's dive into this a bit more and look at, and then there's a summary here as well of this that's kind of nice, because it just uses the keywords here. So the outermost one here is the domain, then what's called the abstraction, which I'm not going to go into, but then the idiom and the adverb kind of as the main items. So some of the questions that we ask as research questions, before I get to actually the actual papers in a second, are things like this. How do we best display data of type X? So we have categorical data, for example. We have data that has a lot of time in it, that has maybe durations and so on. So things that are unusual perhaps, or just difficult, or just things that people need for particular tasks. How do we even do that? Then there's always this question of, how do we compare things? Is technique A or technique B better at a particular task? And then how do you measure that? So things like, also, and of course, what are those tasks? There are things like comparing data over time, finding correlations, finding outliers, lots of things like that. What are the properties of a technique? So how does it even work? So this is the more fundamental question. It's very easy to put two different things in front of people, watch how they work, and see who solves a problem faster and maybe finds it more compelling, the technique more compelling. But then why is that the case? That's actually a deeper question, and that's the next question. And then how can we improve interaction? How can we improve how people work? How can we use what we learn in one study and use it in the next one? And then there are lots of ideas around where people have been doing things for many years, and sometimes it's worthwhile to revisit those and actually look at those and say, well, did this actually work? How did this work? Why did people use that? And can we learn from that? Can we use that for new ideas? And I will get to that at the end if I'm not running over too much with my preliminaries here. So to jump right into it, there's one very, very famous paper in data visualization that is called Graphical Perception, Theory, Experimentation, and Application to the Development of Graphical Methods, that Bill Cleveland and Robert McGill. This was published in 1984, and it's a very long paper. I'm not going to go into much detail here. I'm going to show you a few simple examples from what they did and what they found. But it's a good illustration also of the kind of research people do, and it illustrates a little bit the kind of discussions that people have in this field. So what they did was basically look at a large number of techniques, certainly things that people had been doing at that time in statistical graphics. So Bill Cleveland comes from the statistical graphics area, and he's still actually active in that area. And he wanted to look at some of the things that people were using that in the field itself, or that he saw people use out in business and see how well they compared. And one of those, of course, was bar charts, and he also looked at line charts and a number of other things. And he had a number of tasks. So I'm going to show you very briefly what those tasks are. This is a fairly confusing paper because the tasks are all labeled with numbers, but I just want to show you a few of those. So the first one here is called type 1, which is there's a bar chart, as you can see, and there are two little dots over the A that you hopefully are able to see. And the question is, what's the difference between the two? So how much larger is the second one than the first one? And there are different kinds of judgments here, relative and absolute ones. So you could ask, what's the value of the first point, for example? In this case, it's a comparison task. But you could also point to one and say, well, what's the value? What's the value of the left one, for example? The left one has a dot. And see how well people do in that and how well they can compare. And there's another type here. There's a type 2. Here you have stacked bars. And again, you see little dots. And the question is, which one of those is larger? And then also, what's the difference? So how much larger is B than A? And then type 3 here, there are multiple bars in between those dots. So there's A and B, and you can see a little dot there over the A and a little dot over the B. And the question is, which one of those bars is higher and how much more? And in this case, it's pretty obvious which one is higher, but there are also cases that are a bit harder. And again, the precise difference is hard. And so the way this was done is that those would be printed on a piece of paper, and people would be handed about, I don't remember how many, but some number of those sheets, 20 or so. And they would then fill in with a pencil what the numbers were and then hand them back. So this is the way these studies were done in the past, that you would just sit a number of people down, have them do the task, and then evaluate the results. And I will talk a little bit about how this works today as well. Then there's this type 4 here, which is again stacked bars, but now the dots are in parts of the bars that are not at the bottom. So they don't have a common baseline, and that actually makes it harder to compare. So I said this in my little description of the talk, that it's harder to read these bars when they are stacked because the baselines aren't the same. And so you're now comparing length, pure length, rather than length and position, because they don't start at the same point. And that actually was found to be much harder than when they were on the same baseline. So this is one of those things that people learned at that point. And before 1984, people didn't really know that, or they hadn't done this in any kind of systematic way. So that's why this is a very important paper. And then the last one here is the two dots are on the same column here. So you're comparing two bars that are on top of each other and over the A, and so you can see that would probably be even harder to do, and it turns out that actually is the case. So they found a number of really interesting things about very, very simple techniques like the bar chart, and tried to actually put some science behind it, tried and showed and clearly showed and succeeded in this, in showing that some of the things that people were thinking were true actually were true, and but also showed some of them actually not be true. One of the things they also looked into is a bar chart, is a pie chart. Sorry, a pie chart compared to a bar chart. This is an old discussion actually that goes back at least to the early 1900s. So there are papers, and I will show you this in a second. They actually cite some papers from the 1920s, but there's a discussion even earlier than that in Will Britton's book from 1914, where he discusses those pie charts and how he did not like them. And the question here is basically the two examples are obviously here a pie chart on the left and the number of bar charts on the right. One of the bar charts corresponds to the pie chart, but the task was actually not to find that, but to sort them. So to sort each slice, or the order of those slices, or the order of those stacked bars, from largest value to smallest value. And that is much easier to do certainly in the bar chart than in the pie chart example. And what's nice here about this is also that they actually write in the paper basically that it was easier actually, but the difference wasn't very large. And so, and you can see some of those papers being cited here that's in those parentheses where it says EOS 1926 and so on. These are papers from the mid-1920s. But they also say that we conclude that neither graphical form should be used because other methods are demonstrably better. So they were kind of saying, well, just don't do this, just use other techniques that are better. And so their main argument is to say, well, stacking bars is nice, but it's hard to read, and pie charts are actually really bad at many things. There are reasons there are cases when they're actually good. I don't want to go into that much right now because I'm running over a little bit, but I want to get to the other examples. But the main thing here was their main point is to say, well, just use a bar chart and sort the bars, and you will be able to see the differences quite well, which is true, but it doesn't show you the part-whole relationship quite as well. But anyway, the scientific field of data visualization also has its little quibbles and little fights in there. And sometimes you can actually see that when people are a bit snarky in their papers. Even statisticians in the 1980s were actually doing that. So what I just described is the way studies work and the way science to a large extent is done in data visualization. You have to figure out how to compare things, and then you have people actually do tasks and you watch them. And those tasks tend to be very, very simple. The reason for this is that it's hard enough to figure out what's going on when you have a very simple task. When the task gets more complicated, it's impossible to actually suss out what the differences are, where they're coming from, and so on. So the way this was done until a few years ago, until maybe 10 or so years ago, was in the labs. You would recruit, very often these were students, to university students, to sit down for anywhere between 5 minutes and an hour, and just give them a stack of paper and have them work through lots of questions, like in an exam basically, and measure their performance, measure how well they were doing, how fast they were, and then ask them a few questions. There's a big change that happened a few years ago. I don't actually know when Mechanical Turk started, but there's this system that Amazon has that is called Mechanical Turk. And if you've heard of that and you're confused by the name, the reason is that there was this automaton, I guess, that was built in the late 19th century, I believe. It's supposed to be played chess, and it had this figure on the top that had that was dressed in these Turkish clothes, and so they called it the Turk. And the Turk would play chess against people and would usually actually win. But what actually happened was that there was a small person hidden inside that machine that was actually playing chess, that was actually doing the playing. So this was not an actual machine that could actually do this, but there was a person hidden inside. So basically the machine was pretending to do, or the person was controlling the machine that was pretending to be smart. And the idea behind Mechanical Turk is that there are tasks that machines just cannot do or are really, really bad at, that people can do really well. And so why not let people do those tasks? And Amazon uses this for things like, does this description match the picture? So the description is about a hammer and the photo shows you a USB stick, then you can very easily say, well, this is wrong, whereas a machine would be very bad at this. And a while ago, people have figured out that this is actually a good way to also run studies. You could actually ask people questions and have them solve little problems and pay them a little bit of money. This is also, that's actually part of this, is that these are called micro tasks. And what you do is, and it's also called crowdsourcing, I suppose. It's not a very precise term there, but the micro tasks are small things. So you solve lots of little things. You look at lots of pictures and compare them to the descriptions, for example. Each time you do that, you earn a cent, or you earn a very small amount of money, and you do lots of them very quickly, and that way you earn a few dollars an hour. And that's also why it's possible for academics rather to do this, because you can run these fairly cheaply, and you can run lots of them. So you can have 100 people in your study pretty easily without that being an issue, because it's hard to recruit 100 people and actually run the study with 100 people, because just the time commitment is very high. And so here's a paper that talked about this. This is from 2010. Jeff Hare had done some work on this. Actually, he did some work around the same time on using Mechanical Turk for this. And he looked at basically reproducing some of the tasks that Bill Cleveland and Robert McGill had used in this 1984 paper. So they were reproducing some of the work, which is important for science. So in science, there is one part which is you do a study or you show that something is the case, but then other people have to be able to reproduce what you've been doing for it to really become accepted fact. And it's not being done that much in visualization so far, but this is one of the few examples where this actually has happened. And what they were doing is they were building on top of that. So that you can see here, this is a figure from their paper that they did these tasks. They looked almost exactly the same as the ones that Cleveland and McGill were doing, but they also added a few additional things, like they added this bubble chart at the bottom left there, and they added a tree map, and did more of those comparisons, and that way shows that their results using Mechanical Turk as so this online platform as the mechanism very closely followed what, and they got the same results essentially as Cleveland and McGill had gotten 25 years earlier, and they were also able then to expand this to say, well, here are some new results that they just hadn't gotten to because these were not things that you would have asked about. Like tree maps didn't exist in 1984, so they were able to add a few more things. They also added some interesting things there that have to do with screen contrast and with things that you would not do on a black and white printer anyway. Like, for example, there's this contrast study here where they looked at how strong or weak the background contrast, or the contrast between the background object or the background and the foreground object can or should be, and also with the grid lines, how strong grid lines need to be so that they're readable, and when they get in the way, and also how this correlates with the number of objects. Because you can imagine, as you have more dots on your scatter plot, you're going to cover up more of the background, and so you won't see as much of the background, so you might have to make it stronger. And they found some interesting results there as well. So this is a very, maybe you will think that the Cleveland and McGill one was a bit theoretical, but you can see that there are also very clear applied ideas here that you could go into any program where you can change the background of a chart and change that background and maybe use their results to actually tell you what that background could be, or how strong to make the contrast between the background and the grid lines to make it as readable as possible. Excuse me, for maximum readability. So Mechanical Turk is a very useful platform. It's not the only one, but this is the one that's used by most people. And there have been some other approaches to crowdsourcing, but I think all of these studies that I'm going to show you now are using that. So these are all recent enough that they're all using Mechanical Turk, as far as I remember. Here's a paper that I like because it's a very interesting study that showed some very, well, most of these results are kind of, they were kind of expected, but some of them were quite surprising. And I want to show you briefly what this was about. This is a paper from 2010 or so, 2009. And I think this was actually done on Mechanical Turk before even the previous paper had been published. But they were looking at how scatter plots and parallel coordinate plots compare in terms of judging correlation. So what does that mean? Here are some examples of scatter plots, and they are the horizontal axis here is the strength of the correlation. So the center column here, so this is the fourth column from the left, has dots that are not correlated. So there's a zero correlation between them. They're just randomly distributed. And all the charts to the left of the middle column and to the right have stronger and stronger correlations, positive and negative. So negative means on the left there, that means that the value being higher on one axis means that it's lower on the other axis. So you get this diagonal going from the top left to the bottom right. And in the other case, the ones to the right of the middle have a positive correlation, which means that the values on one axis being higher means that the other value also is higher. And then there are three different levels here, horizontal rows here, that each has a different number of points. So you have 10 points, 40 points, 160 points. And among the hypotheses was that they were expecting people to do better when there were more points, which they actually found was actually the case. So this is a scatter plot, and a scatter plot is very commonly used when you want to judge correlation. And so it's not a surprise that this would work, but what they wanted to actually do is they wanted to compare it to what's called parallel coordinates. And parallel coordinates are a very close relative of the scatter plot, actually. The way they work is that you have these lines that are not like in the usual coordinate system at a right angle, but they're parallel to each other. And so each set of lines that you can see here is one of those plots. And the order is the same. So the values are the same and the orders are the same. So you can see that the middle column here has these three plots. And each of them has lines going left to right, and the values on each of those axes are mapped. So if there's a value of 7 on the left one and 8 on the right one, you would have a line going from somewhere along this axis to a slightly higher point on the right axis. And you would do this for a number of points. So in this case, in the top row, there would be 10 points. In the middle row, there would be 40 points, data points, that is. And at the bottom, there are 160. And when you look at the leftmost column, you can see this cross. You can see how the lines are all crossing and kind of meeting in the middle. And that's actually really important for judging correlation. But that's negative correlation. So that means that the values that are higher on one axis are lower on the other. And the ones to the right that are correlated are more parallel to each other. So you can see that there are fewer and fewer crossings as you go from the middle out to the right. And that's a hint basically about correlation. And so what they found, I'm going to show you some of the examples here, but I realize it's going to look a bit scary, but it's actually not that hard to read. And I also want to show this because it's interesting that even a really good paper, so I really like this paper a lot. This is a really, really well done paper. But even a really good paper can have really horrible charts when they're showing their results. And so this is an example of that. What this shows you here is the scatterplot results, which is that they have an axis here. The bottom axis is, or the horizontal axis is the C-score, which is the correlation amount, and the vertical axis is basically how much their subjects, their test participants reported seeing how strong they thought the correlation was. And what's important here are basically two things. First of all, there's this dot in the middle where all the lines cross, which is really interesting because it means that people could actually see zero correlation really well. So that's really cool. That's really surprising that people are that good at saying, well, there is no correlation here. We can actually tell that. Then as you go out to the left and to the right, you can see those lines kind of following this kind of diagonal pattern, which is what you want. And the further away from zero, essentially, that the line is, the more points there were. So which is also the expected result. So when there are more points, people can tell the correlation much better. And it's actually interesting because people are really good at that. So it's quite amazing how well people can tell the value of for the correlation from a scatterplot. Now contrast this with the parallel coordinates, which has a very interesting different shape, which is that the zero there, so this horizontal value of 0, isn't a point, but there are a number of points here. And so it turns out that depending on the number of points and depending on the C-score, you can actually have people, actually the C-score is 0, but when you have a number of people looking at those, people end up with different guesses that aren't actually very correct. So we're not very good at judging that there is no correlation in parallel coordinates. It looks like there might be even when there isn't, which is quite interesting. And what it also shows is that as you go to the left, where the correlation is negative, the effect is much larger than to the right. So we're much better at judging negative correlation where the lines cross because they're higher on one value on one side than on the other side, and lower on the other side, than on the positive case where they're all parallel, because parallelism is harder to judge. So we're seeing some very interesting differences there. And this tells you something about how and when to use these techniques. So when you want to see correlation, then you want to use a scatterplot rather than parallel coordinates. Now, what's also important, of course, is to understand when techniques are misleading. And part of this is another really good paper. This was actually published earlier this year. Part of the recent developments in visualization is that people are actually paying more attention to what people are doing out in the real world and trying to pick up ideas from that and test those and see how well they actually work. So here's an example. This is paper from CHI, this is the Computer-Human Interaction Conference this year, that had this paper that's called How Deceptive Are Deceptive Visualizations? And the question was, sometimes you see those examples that you see here at the bottom here that are problematic, but how bad are they really? And I'm not going to show you those examples. I mean, not going to go through those examples here, but I have a slide here with the images. So what they did, they used those examples I just showed you on that first slide and kind of turned them into more reduced types because they wanted to get rid of color, because there could be differences in color and so on. And they are looking at they were looking at differences like the slope of the line. They were looking at sizing when you change the size in terms of the area versus the size of the radius when you use bubbles. And then my favorite here is the bar charts that had the vertical axis cut, so they didn't start at 0. And so the question was, if I tell you that, so it's not that they were deceiving people by not telling them. They said, look, here's a scale. It tells you that the value starts at such and such. It's not at 0. I mean, they weren't necessarily pointing out that strongly, but they showed people the values. They weren't trying to keep information away from them. But they showed them this, and then they had them estimate the values from that. And what they found was, and this is another result slide, this is actually a really good one. This shows you how big the error was. So each row here, essentially, each pair of two charts with the same color shows you the same type of chart, but the top one is always the deceptive one, and the bottom one is the correct one, the proper one. And you can see that people, and the interval here is 95% confidence. You can see that people made these very large errors and weren't even in the ballpark of the real value. So they were really deceived very strongly by this. So what this tells you is that you have to be very careful with things like using cropped axes in a bar chart and also controlling the aspect ratio of your line charts and so on. I'm running a little bit behind, so I'm going to skip ahead a little bit. I need to decide here what I'm going to show you and what I'm going to skip. I'm going to show you just one more because I think this also kind of shows this quite nicely, how we can pick things up from kind of the real world and then build on that. Here's a paper that we did. There's a technique that was established, that was thought up in the 1920s actually, and then used throughout the 20s and 30s. That's called isotype. And the way this works is that by, if anybody's familiar perhaps with Otto Neurath and Marie Neurath and Gerhard Arndt, they built this kind of system of images and pictographic charts, as they called them, and they used that to tell people something about the world using data. So they published these books that compared the number of motor cars, telephones, and radio sets in different countries in 1937. So it shows 50 people here at the top, which is the population that they're comparing it for, or this is per 50 people. And then you see the number of cars in the US, the number of telephones, and the number of radio receivers. And then the same thing for Great Britain, for France, and for Germany. And you can see that there are lots more cars in the US than anywhere else, and more radio receivers and so on. And so you can get a sense of the different places and how they adopt technology and so on. So you can read that fairly easily because you can understand what those things are. And you can also read them as bar charts because they just always use the same width. So you can just look at the lengths and it becomes essentially a bar chart. And Neurath was very strong in saying, well, we can't just, like this is about marriage numbers, you can't just scale figures like this because you're going to get distortion. You want to repeat them. And so we did a study that we published earlier this year to say, and this we being my colleagues, Steve Harrows, Steve Franconeri, and myself, and we looked at different ways of scaling things and how well people could actually read those. And we basically found that those charts, those isotype charts, work really well. People can read them really well. There aren't any issues with the images getting in the way. There are even some interesting effects there because there are different effects that basically help you estimate sizes when you have objects rather than size. We also found that what you see on the top, in the right-hand image there, this fish in the background, if you have kind of a chart chunk in the background, so we have an image in the background that's about the same data, but it's not actually labeling, it doesn't actually work, it actually really distracts. So this is a thing that was kind of expected, but it's really a very clear result that we found there. But we also did a different thing. So what I've shown you so far has always been give people tasks and let them do them and then measure how well they do. But in this case, we did something different. We also had them memorize or remember things. So we had them look at an image. So this is illustrated here with the numbers. We had look at number 1, an image that showed them something like about furniture. And then we showed them another one about animals. And then we asked them about the first one. And then we showed them something about about the weather. And then we asked them about the second one. This is called a one-back design. So you always skip one, and you ask about the one before that, and then you show something else, and then you ask about the next one. And that's actually pretty hard. So there are also two-back designs that give you two things in between and so on. And we found that people actually remembered this quite well. And then our last part here is another type of study, which is for engagement, where we looked at what people would actually look at given a kind of a simulation of a newspaper layout or of a website layout, where you have different kinds, like different charts, different text and so on. What would they look at? And so they could zoom in and out and decide what to look at. And we also found that people were much more compelled by the isotype style charts. But there are different kinds of questions you can ask, and there are different techniques for those, depending on what you're trying to find out and what you're trying to learn. So in conclusion, I hope to have given you a little bit of an overview of how research is done in data visualization. This really covered only part of it, certainly. So I want to be clear about that. This covered the part where you do studies, where you perform studies with people to actually learn something about mechanisms, to learn something about perception and so on. There's also a whole huge other part that has more to do with algorithmic complexity and with geometrical modeling and with math and so on, which I'm entirely ignoring here. But the interesting thing about research here is that it's part engineering, part something else, psychology, and all those things. There's a large variety of questions, so there isn't just one thing we do. We do a lot of different things. It's very often answered through studies. That's why I talk about this here. It's not just because I'm doing that kind of work, it's also because this is a really important part. And there are lots of open questions. So I touched on a few of those. So like the whole pie chart question is still kind of open, where we know some things, there's other things we don't know well, how we actually perceive those, how well we can compare things, when it should be used, when they should not be used, and so on. And it's and there are more questions, especially when it comes to color, when it comes to interactions between different things. So there is a lot of complexity we haven't even touched on. And it's also worthwhile to revisit old techniques. So we found that when you look at what people have been doing in the past, sometimes very much based on their design and visual taste or on just ideas about what should be done and what should not be done, that actually sometimes turns out to be really interesting and really quite useful for doing new things with them, like the isotype, which might actually turn into something more applied in the end, given what we found there. And now finally, I want to just show you two books, because in case you want to follow up on this a little bit, do a bit of reading, there are two particular books that I really like here about this topic. There are lots of books about visualization, but these ones in particular talk about research and about kind of the academic side of things and how you learn more about how visualization works. The left one is kind of a classic. This is Colin Ware's book, Information Visualization, Perception for Design, which I think is now in its third edition is what it says here. So third edition, this is I think 2 years old now. It's a very good book. It's always been a good book, starting when it came out in the late 90s, but he's been adding to it, and there's a lot of information in it. Colin Ware knows everything about perception, and he also really writes very well. It's very readable. It's very interesting. So it's a big book, but it's got really an amazing amount of information in it. And then Tamara Munson's book, Visualization Analysis and Design, this came out last year I think in the fall, in October or so. And it's a very different book. It talks much more about this model that I showed you at the very beginning, about what different kinds of questions there are, and walks you through a lot of visualization examples and analyzes those using that framework. And it's a very, very interesting book. It's also very readable and very well illustrated book. So those two are recommendations if you want to go into a bit more depth here. And with that, I thank you for your attention, and I'm happy to answer any questions you might have.
Well, Robert, thank you for that very excellent presentation. I don't think any of us will ever look at graphs quite the same way. We'll get started with today's Q&A session, and I want to thank the audience for their participation. We have a lot of questions that have come in during the presentation, and we'll do our best to get through them all in the time remaining. So during this Q&A session, I'm going to leave this screen up with contact information for Robert if you'd like to contact him following today's webinar. So let's get started. You know, I think the question that seems to be on all our minds is there were a lot of examples of ways to be misled by visualization. Can you give us some general rules about what we ought to be doing? Are there types of visualizations that should necessarily always be considered for certain types of data?
Yeah, so there is one simple answer that I don't particularly like, but that's you can basically never go wrong with a bar chart. So the bar chart is the workhorse really of visualization. It works for a lot of different data, and it tends to be really good because it's easy to read. You can sort the bars, you can do things with the data before, like you can do aggregation, and so you can end up, it's a very, very useful chart for data analysis. Another one is the histogram is what I was going to say next, but actually first of all, the scatterplot. So the scatterplot is one that works really well for looking at numerical data and comparing things to see if there is a correlation between different things, between two things in particular. Also, the histogram is something that's a bit underused, I think, in business intelligence and by lots of people. But the histogram is very useful because it gives you an idea of what the structure of a single value dimension in your data looks like. So you can get a sense of whether you've got lots of high values, lots of low values, whether you have an even distribution or not. And so that way you end up understanding a lot about that data. So it's hard to answer this question in general because there are lots of different things, especially if you have a timeline you probably want, or a time axis, you probably want a line chart. There are issues with line charts because the scaling can be hard and so on, but there's certainly those basic techniques like bar charts, line charts, to an extent area charts if they're not stacked, histograms, and for more complex things, perhaps if you have lots of values, then a tree map can be a good overview. The thing with the pie chart in particular is that it's used by lots of people for things that it shouldn't be used for, especially when things don't actually add up to a whole, or when you have lots of values. So if you have more than 5 to 8, it's probably too much. So those are kind of very quick, very general guidelines. But depending on the data, there are much more specific ones, certainly.
Robert, thank you so much. We have a lot of very specific questions coming in about different types. One of the questions has asked to please see the names of these books again. So I'm going to put your last slide back up and give the audience a chance to write those names down while we're talking. But let me ask some questions about some types of data that I don't think were reviewed in detail. For example, the use of color and bubble charts, or particularly bubble charts where more than just X and Y axis is being described, but also, for example, where the size of the bubble describes a third variable. Can you comment on those?
Mm-hmm. Sure. So color is a huge topic, and you could do entire talks and entire seminars on that. The main thing to remember is that what works well is when you have a small number of distinct objects or distinct categories and you label those with color, and that number is no more than about a dozen. Actually, it's more like 8 to 10 that you can really tell apart really well. So that pie chart I showed you at the beginning with the 50 different colors is just entirely impossible to actually remember those numbers or those colors. So color, and again, there's a lot more to be said. Color that's continuous. We can really only read a small number of different values, probably around 5, if you're lucky. Really. So color is really hard, and it's really difficult. And you should probably think or look at things like what's called Color Brewer. There's a website called colorbrewer.org that has some good resources for that has color palettes to use. And in general, just use colors for labeling for categories. Bubbles are a very different issue when they're used on a scatter plot. So I think what you described was 2 axes that had mappings or that were used like in a scatter plot with the bubble size for a third value. That can work when there is a correlation between those 2 and the third axis, because you will see that those bubbles, the different sizes, will actually end up in certain spots. But when the correlation is low, or when there isn't one, especially, and you're looking for things in there, you're going to find that it's very, very hard to really understand what's going on, or if there's too little correlation between the first 2 axes. So that really makes it hard. There is a technique that's called the scatterplot matrix, which is basically a small multiples version that compares a number of different axes in a grid. And that can be really good for looking at more than 2 dimensions at the same time. And then, of course, you also want the interaction in there. So it's not just about showing this, but also being able to select a part and seeing how it highlights in a different chart and so on. So you can understand what the relationship is between those two axes in one chart and those two other axes in another chart, where those same points are high up or further down and so on. So that's a very brief answer to that.
Obviously a very complex topic, and questions continue to come in about particular types. I'm going to put your email address back up so folks can see that. We have a couple of questions regarding the level of support that Tableau provides for R and Python, and whether or not Tableau provides visualization beyond what R and Python provide natively.
Yes, so there, okay, so the first part of this, there is an R interface. So you can use R to do modeling and analysis. And the way this works, I don't want to go into much detail here because it's kind of off topic for this particular talk, but the way this works is that data actually is queried by Tableau, is sent to R, so it's coming from whatever database it lives in, is sent to R, R does whatever you tell it to, and then the results come back to Tableau and are visualized. That's the way this works. This doesn't work directly with Python. There's a way to use Python to ingest data, but not directly in the program. And in terms of types of visualizations, Tableau covers a lot of the things that are useful in data analysis. It doesn't do everything that R does, because R lets you do there are like 1,000 different packages for graphics alone. So you can do things in R that you can't do in Tableau, but it's much harder to do them. And it's much harder to do interaction, certainly. It's pretty much impossible. And of course, it's much easier and quicker to just switch between different things in Tableau. So R and Tableau have lots of different strengths that can be complementary.
Well, thanks. You know, we have a design question that's come in that's kind of interesting. And the question relates to the fact, boy, this person is having a difficult time choosing between different design alternatives for their visualization. Would it be okay just to ask the users which they understand better, or does that lead to some risk of misunderstanding?
Yeah, that's a good. It depends. So in general, I would say sure, show it to the users. I think that's a really good idea, because that's how you test things. If one of them is very familiar, so if you're using something that people have done before and one is new, then there can be a bias towards the old thing, because people have seen that before, they are familiar with it, and the new thing is unfamiliar and can be a bit scary. It also depends on how comfortable people are with this. So I would say, unless you're really worried that people are just going to pick the shinier one or the one that they're familiar with, I would just ask the users. Yeah, definitely.
Can't get in trouble that way. One of the things that particularly interests me in these days, when we're building visualizations that we're presenting simultaneously to audiences around the world, and in the Americas and in Asia and in Europe at the same time, does your research point to any cross-cultural differences in how people perceive data visually?
Oh, yes, definitely. There are different, and this is actually a very interesting area that hasn't been studied much. But we know a few things, especially because just looking at what people have found in psychology research and in ethnography research. But there are differences in color, certainly. So the meaning of colors, like what does red mean, what does black mean, what does white mean, what's good, what's bad, can be quite different, can be the opposite in different cultures from what you expect. So that can be really, really difficult, really important also to get that right. Also, the reading direction, which is different in Hebrew and Arabic. So if you're talking to people who speak those languages, sometimes. So I know that in Israel, charts are left to right, even though the writing is right to left. But in the Arabic world, numbers are written right to left. So I think that their charts are also right to left, but I'm not entirely sure when the axis value increases. So yeah, knowing that is very important, and there's very little research that I'm aware of in this area. But that's a very interesting question for sure.
Oh, lots of room left for study. Well, Robert, thank you for some great answers to some very good questions. And for those of you who asked questions that weren't answered today, we'll be sending them to Robert and the Tableau team so they can follow up with you directly after today's webinar. I do just have a few quick announcements before we sign off. Please mark your calendars for August 18th. That's our next Data Science Central webinar, which is when is the right time for real time? Architectural Best Practices for Hadoop. And that's going to be sponsored by MapR and Think Big, a Teradata company. Also, today's taping will be available for on-demand viewing later today. and can be found on the home page of Data Science Central in the Webinar tab located at the top of the page. Well, that brings today's webinar to a close, and I'd like to thank our audience for their attendance and thoughtful questions, and a special thanks again to Tableau for their sponsorship, and our speaker today, Robert Kosara, for his insights into this really interesting topic. My name is Bill Vorhies. I'm very pleased to have been your host for today's event, and I look forward to seeing you all again on August 18th. Have a great day.